Hello everybody, welcome to microbenchmarking, a deep dive. First of all, it's very intimidating to stand in front of this huge screen, but the good thing is I have a lot of source code, and because I got complaints at DOFWorks Poland that the source code is way too small, there's too much source code in it, this will actually fix it. So this is cool. If you want to have more time for a slide, or you want to zoom into the source code yourself, there's the link to the presentation. You can actually view it live if you like. Just swipe through it. There will be more links throughout the session, so if you want to actively participate, feel free. The other thing is, I will probably ask questions. Please don't be shy, just yell, give me your response. Because it's a deep dive, we have so much time, and just me standing here talking the entire time might be slightly boring. So I will kind of challenge you once in a while and ask questions. So the guy here, that's me. I'm probably one of the older dudes in town. Who has started with Java 1.0? Oh, I'm not the oldest guy in town. It's so great. Typically, I don't get any hands. Excellent. So yes, I started with Java 1 at the university. I have seen 1.1, 1.3, 1.5, 1.8, and then the rest of all the others. So I'm a programmer since '89. I'm studying computer science, or as the Germans called it back in the days, Diplom-Informatiker. Do QA and testing since '98. A lot of performance testing since '99, and I'm one of the co-founders of Acceptance, and you find me on Twitter. I still call it Twitter, and Mastodon. And yes, if there's something besides IT you want to talk to me about, it could be bread, sourdough bread, for instance. We can share recipes if you like. And then someone paid for the trip here, obviously, and someone also pays for my daily living. And this is this company called Acceptance. We are a small German software testing company, which is a subsidiary in Cambridge, Massachusetts. We do mostly all kind of quality assurance work, in parts also performance testing. And because we do performance testing, we have a tool called XLT, Acceptance Load Test, which kind of is a different kind of G-meter. It's all Java-based. We have to create a ton of load. You run into issues. You have to optimize it. And the target systems are often Java-based. You run into issues. You have to optimize it. You have to diagnose stuff. Most of the knowledge you will hear today is coming from practice. So I really ran into all of these issues, really experienced all of this. I really built my own GDK. Who ever built their own GDK from source? Okay, one. So I had to build my own GDK just to see if a patch works, stuff like that. Good. By the way, obviously, we learn from each other, and I learn from these two guys the most. Alexei Shipilev, he will be here tomorrow probably. He's working for AWS, for the GDK team, and Douglas Hawkins, he's currently at Datadog. He was at Azul Systems before, and they have great talks and websites, stuff like that, about performance, tuning, all the nitty-gritty details of how actually synchronization works and concurrency and stuff like that. So I really highly recommend to keep this slide. If you have to keep one slide, keep this one. Not mine, theirs. There's way more entertaining content. Good. And because these guys gave their knowledge away for free, I do the same. Everything you find today is Creative Commons licensed, so you can do whatever you like with it. Just attribute me, that's it. If you want to use it commercially, fine. Everything is cool. Enjoy. The source code is Apache licensed. So all source code today, all open source today. So what's actually in this deep dive? And I'm kind of a little surprised, by the way, by the deep dive concept, because it's not a workshop, but it's also not a talk. It's something in the middle. So I have partially a workshop where you can actually really do stuff yourself. There will be a Git repo you can clone later on if you like. And you can really run some of these benchmarks on your machines. I might ask for results if someone has the time, just one of these two benchmarks and give me some numbers, especially guys with Macs. I'm a Linux dude. Guys with Macs, If you see other performance numbers, it would be great. Good. So today we want to basically get a feel for microbenchmarking, and we will kind of figure out what microbenchmarking is in a few minutes and discover why you might or might not need it. We will learn about the Java microbenchmarking harness. We will learn about typical mistakes, about hardware and JVM insights. You will actually see assembler code today, something a typical Java developer won't see at all. And we will also talk about kind of why hardware is hardware and how does hardware actually interact with your Java program. And I will give you basically some good and ugly stuff at the end of the day so you can take it home and then decide if microbenchmarking is something you have to use. By the way, everything today that's a problem, a mistake, an approach, hardware, JVM, applies to your daily work. Even so you won't microbenchmark at all, everything is a takeaway today. So all the details about why and why not applies to your daily work as well. Oh, was already too boring, sorry about that. Good. Oh, you just changed seats, cool. So there's one reason why this presentation talk exists, and this is medium.com. Sorry about that. If you Google and you basically ask for microbenchmarks and information, you obviously often end up with medium.com. There's really good stuff on Medium, and sorry if you write for Medium, not blaming you personally, but let's say 90% of the content on medium.com is not even medium at best. And therefore, there's so many microbenchmarks you find there, and I say, oh, you should do this, not that, because here's a microbenchmark that proves that this is better than that. So I got really frustrated and annoyed, and just came up with this talk. Some of my customers wasted weeks tuning stuff, really, oh yeah, this is twice as fast. They shipped it to production, nothing changed at all, because nobody understood the concepts of the JVM, and what they did locally didn't apply to production. So it's one of the others. And many people just say, oh, let me tune, and then start to change things without diagnosing first, coming up with an idea, a theory. So this also tries to do the same today. We just try to develop a theory first, and then we go into details. And of course, some of the stuff is fun. And by the way, the first couple of slides will be filled with car analogies, because one of my mentors was kind of a car nut. And at the end of the day, I always try to translate problems into something he can understand. This was basically something with cars. So we will see some car-related things just to explain why microbenchmarking is important. So boring stuff first. And it will be more interesting soon. If you want to do some of these benchmarks today, everything you find on the repo, Java, Maven, Git, some Java IDE, command line, and if you're a Linux guy, you can install Linux perf in hs.this. The later one is for disassembly. This is really basically then already a very deep dive if you do that. Good. So what is a benchmark first? Of course, there's Merriam-Webster, and Merriam defines a benchmark as a study, something as a competitor's product or business practice. Okay, that doesn't fit. A point of reference from which measurements may be made. That could be us. And there's a last one, is a standardized problem as basis for evaluation or comparison. This is what we are going to do. So this is a benchmark. We have a standardized problem, and we try to evaluate and compare. Or you take a car, maybe a racing car, on a track, you race around, and you measure time. It's actually the same. So what is a microbenchmark? You basically simplify everything you have done before. Instead of taking a car to the track, you just basically take the engine out, you put it on a test bed, and you just run the engine instead of the entire car. Or you take the tire, you put it on a tire simulator, kind of a machine, and you try to simulate things. So you make everything quite small. And that's basically unit testing, but as benchmark. So it's the same idea. You do something in a defined way, you can repeat it, you should always get the same stuff. That's, let's say, microbenchmarking is unit testing with numbers. Of course, if you simplify things, this will be what all this talk is about at the end of the day. You simplify and you get side effects and you get drawbacks. One is obviously your environment is different if you're, once again, cars. If your engine is on a test bed, it's not outside, it's not raining, it's not sunny, it's not changing the temperature, it's just sitting there and doing its thing. So everything you do is also kind of simulated. You assume certain things when you run the engine. And you might remove things that could be the cause. So instead of, let's say, having an airflow that's coming and going because you accelerate, you de-accelerate, it's just the constant airflow at the end of the day when you have your car on a test bed because there's a huge fan blowing. You might actually remove things you don't even are aware that they exist. And this is the biggest problem at the end of the day with microbenchmarks. Because you might just try to get to a conclusion, but you can't because you actually remove the problem in the first place. Of course, there are less interactions. There, for instance, there's no transmission at the end of the day. There is, the way the thing is installed is different, stuff like that. And of course, you develop a bias. If you just watch the thing and you say, oh, this is great. If I rev it up, I will be definitely faster. And you go with this bias into your daily life. And this is what microbenchmarks on medium.com usually do. They give us a biased opinion, and this is what you should do all the time under all conditions, period. So, yeah, of course, racetrack, tires, petrol, all these things. So, and now let's make it a little bit entertaining. Let's start with a couple of numbers. The first numbers, oh yeah, that's good source code. It's really, really simple Java code, and we benchmark. We benchmark an array copy because everyone says, the internet, of course, source of general wisdom, you should use array copy all the time. Never do manually copying at all. So what I do is, I have two arrays, I do an array copy, and then I do a manual copy operation as well. And then I just measure the time and just see what happens. So, any ideas what kind of numbers we might get? If you've peeked into my presentation, obviously, I should kind of don't say anything, but anyone kind of, let's say a difference between the first and the second one in factors.
Probably very little.
Very little. Okay. So system copy gives me 1,900 nanoseconds, or in the second case, 1,200, and manual copy is at 2.5 times the speed. Sometimes not 1.5 times, so it's kind of give or take. But, the internet is right. Always use array copy because everything else is crap. Okay. Second one. We have the famous one, never concatenate strings yourself. Don't do A plus B. This is bad. Do a string builder, and if you do it right, you use a size string builder. You always kind of indicate what kind of final size your string will have. So we have here this nice benchmark. First part, a string builder. We do a couple of appends. We actually append 2 strings and a number. Then we have another one that says, is this a little blurry for you? Kind of? No? Okay. Then the next one is we pre-size. We already know how big it will be. So, and we do our appends. And the last one is A plus B plus C, the one you shouldn't do. Any kind of ideas of differences? Between the last and the first, maybe? Okay. Yeah. So if you do a pure string, it's 2,500,000 something thousand nanoseconds. If you do a string builder, it's 43,000. And if you do a size string builder, it's 5,500. So the internet is obviously right, as George Washington already indicated correctly. The internet is always right. Pure string usage is bad. You should always do a sized string builder. So the internet is right. Good. Last but not least, and please always indicate if this is a little bit too small, I can size it up. We have an example of streams and parallel streams, because everyone says streams are bad because they're extremely slow. You should never do streams. So I have a stream example. It's a very simple one where we do some nuts calculation here. So this is just a calculation that is kind of a little expensive at the end of the day. So we have a loop that multiplies stuff and adds stuff up. We do this as a stream based on a couple of longs. We do this manually, and we also do a parallel stream. That's the famous one. By the way, this is in here because I have seen in the source code for a benchmark done by my crew all the streams, and there's always a dot parallel in it. And I think they might not have gotten what this actually means at the end of the day. So, ideas? No? Okay. So, manually computing all of this is 5,800,000. Doing a stream is 23 million, and a parallel stream is 10 million. So, in that is right, never use streams because they're awfully slow. And if you have to, do a parallel stream. Interesting question is, this thingy here is an 8+8 core notebook. And this is only twice as fast, the parallel stream. It's kind of fishy, isn't it? It should be faster, but it's not. Okay. But the internet, once again, is right. Don't do streams. Good. So, of course, everything you have seen before is garbage. It's extreme garbage, extreme garbage. But it confirms the internet truth. It's nice Java code. Nobody can say anything about that, but so what could be wrong? Any ideas?
There's no warm-up and there are no optimizations and the garbage collector can get in the way.
Garbage collector, no warm-up, no time for optimizations. First one, anything else? Clock? Good. So, okay, let's get into that. First, I want to set some goals. And these are basically my personal goals when benchmarking. I want to have something that's repeatable, easily. It shouldn't take that long to repeat the same run again. I want to have something that's predictable. So if I do the same thing again, it should actually yield the same result. If I do it again, it should yield the same result, which is similar to repeatability, but here in this case, it's in terms of measurements. I would like to have something that's easily changeable, so it shouldn't take hours to come up with a new idea or a variation of the topic. I want to have control over the parameters going into the test, as well as its environment. I want to have something I can use for debugging, kind of a profiler, debugger, some things like that. I want to have something that's easily understandable. So if I have code that nobody can read, doesn't make any sense because I can't share it. I might be the only one that understands the code, but I'm probably the only one who thinks he understands the code. It doesn't mean I understand when I think I understand the code. No? It's a different topic. And of course, the true goal is I want to have something where I can learn. There's a knob I can turn. If I turn the knob, something happens. I can measure. If I turn it back, I can measure. If I turn it back again, I get exactly the same thing. So this is what we try to do today. And of course, you can Google something for microbenchmarking. You will almost end up with the same tool. If you Googled, let's say, 7 years ago, you might have found a second tool, which has been abandoned because it was garbage, because all the measurements there were kind of really, really obviously garbage. So if you have to measure something that takes, let's say, 15, 20, 30 seconds, something, or 60 seconds, you can leave the room because you will never need any microbenchmarking knowledge. This is completely fine. 30 seconds, just do whatever you like. You can't be wrong. And if you want to microbenchmark, obviously you don't have to reinvent the wheel because someone else spent all the time doing something. And there is a proven tool chain, and this tool chain is called Java Microbenchmarking Harness. It's open source, maintained by a large community, and by Alexei Shipilev, and you can ask him all the questions tomorrow. And it's built to really address all the shortcomings of typical benchmark frameworks. And it's used to validate the GDK performance for all the tunings, all the changes that have been applied or will be applied, or if you come up with a change and you claim that's faster, prove this with a microbenchmark. It comes with really, really nice built-in tools at the end of the day as well. So we'll see all of them today. Good. And so the question is, yeah. This is not going to be an extensive GMH training. There might be other trainings that give you more, so I might skip over certain things and just mention them. But of course, Google is our friend, or any kind of, I have to drop this word once, AI framework you can ask, like ChatGPT, something like that. They will probably explain certain things kind of nicely, but they probably won't write really, really, really good microbenchmarks for you. And there's a famous saying, and please apply this to your daily work constantly. A fool with a tool is still a fool. Applies especially to everyone with a Jira account. Because, you know, it was once a very nice tool, but once it got into the hand of the wrong people, it turned into a nightmare. So, good. Then let's benchmark. Our first benchmark, and by the way, please ask questions. If you have questions, ask questions. It's not a one-way street, once again. So this is the first simple benchmark. What we see here is kind of JUnit for benchmarking. There's a setup method. It's not before, it's setup. There's actually test method called benchmark, annotated with benchmark. And there's a little bit of ceremony around it. It says how long should the warm-up be, the measurement time, how many forks, I will explain this in a second, how you want to benchmark, and what kind of state you have. So that's the simplest version of a microbenchmark. And when we run this, we run setup first, and we'll talk about setup later as well. Setup first, we will define a time, just a random number at this moment, obviously. And then we do an addition of time, a multiplication, and some other things. Obviously, method naming is not my strongest, so good. You should always run your benchmarks with Maven. And of course, someone said and posted, do a Maven verify. That's enough. When you do microbenchmarking with GMH, you might want to do always clean verify. In 99% of the cases, a verify is fine. But if you just start your benchmark right in the middle and you do kind of a Control-C, you might get into a very strange state of things on disk. So I always clean stuff because I sometimes burned a couple of hours finding why something doesn't compile anymore. It doesn't make any sense. So clean verify is my go-to way for building the benchmark. GMH is magic. It creates code for you. It wraps stuff. The code you see is not actually just the code that's executed. It comes with something that does really a lot of magic. So it generates, annotates code, and ends up at the end of the day with a benchmark jar. And when you call it like that, Java jar target benchmarks, you can define which benchmark of yours you want to execute. It's nothing else than a regular expression. In this case, I want to run A01. As you can see here, org xc gmh A01, that's the full name. You can just use the short name, and then it will be executed for you. The first part is the warm-up, defined as 5 times 2 seconds. And then iterations for measurement, 10, each 1 second long. And this is what we get. And of course, the first question should be, just staring at the outcome, what would be your first question? Why is the warm-up faster? And we will not solve this problem, but try to explain it during this talk. So this is the first part that's very confusing. And I will actually ask Alexei about this tomorrow, because it happens often that the warm-up actually is faster than the final result. But overall, it's an okay benchmark so far.
For the warm-up is because it's using C1. When you have the first compiler, it tends to be more chiller in terms of CPU usage. So it depends on how much CPU available.
One of the probable things, as pointed out, is we have 2 compilers, C1, C2, and there might be a different path of optimization that has been taken at the end of the day, and we'll see what has happened. Good. So I just hit you with a lot of numbers, because when you benchmark, don't benchmark once and go and have dinner, just do it again. So on the left side, you see the first result, and this is all on this crappy notebook here. You see, we start with 0.6 nanoseconds, and then it's very constant during iterations. The next one is just the opposite. It starts slow, and then it turns out to be faster. Right in the middle, it's just, I don't know, and continues. And the right one is kind of the left ones combined. These are not made up numbers. I really measured and copied. It's not me having a number generator here running for you just to entertain you. This is real. This is what happens. So it's confusing. It's not usable at the end of the day. And this is what microbenchmark is. It's mostly confusing. So we have to find a way to understand it and make it less confusing. So I switched from my machine, that's an AMD T14S Lenovo notebook, to a hoster in Germany called Hetzner. They have very nice machines and they're very cheap. If you pay $400 for a Google machine, you get this at Hetzner for 50. And you actually get way more performance. They don't have this huge Kubernetes landscape and all. This is kind of almost bare metal cloud hardware, but it's way faster and it's way cheaper. So if you are looking for something to optimize, just try out Hetzner. They have data centers in the US and Germany, as well as Singapore, and Finland is another one. But I'm not sponsored by Hetzner. I just basically visit them 2 weeks ago and saw their data center in Germany. The guy gave a huge tour, and it was really, really nice to know. So here we run this at Hetzner, and as you can see here, we have really, really nice results. Overall, this is perfect, almost perfect. So of course, there's a little bit of jitter. We get to the nanosecond part in a second, but it's really nice. So I switched basically from one machine to the other. The numbers totally changed, but they are now stable. What I would expect, kind of the warm-up is kind of comme ci, comme ça, and then almost constant numbers. Cool. Might have just to use another machine. Does anyone have cloned the repo and is able to run? Could you do me a favor and run A01? Anyone with a Mac? Oh, you have a Mac. Good, good. So while you run this, and just yell when you finished, or when your computer finished. Our first learnings. First, never trust the first result. By the way, never trust the second and third either. Always run it multiple times. We have a result. Okay, so 0.3 give or take. Okay, which is interesting because this one here is kind of very shaky. In 1 nanosecond, it's almost kind of like the Hetzner machine. So this is an ARM machine. The other one was an x86. Cool, good. So never trust the first result. Always run the test multiple times. We already have seen how easy it is to get confused. If you have a second machine, get yourself a second machine. And if you get yourself a second machine, don't get the same model and don't get a laptop. If you already have a laptop, get a desktop machine. Get something that's different. And please don't show up with Windows machines. For serious benchmarking, it has to you have to have a Unix machine. Sorry. If you have access to the future target system, run the benchmarks there. It would be perfect. And it will be even more confusing, trust me. And now the question, does it really make sense to run a benchmark that just gives you a 1 nanosecond result? Yes? No? The rest of the people are still confused. Good. Just one thing. If you want to debug your benchmark, you can add this main method, and you can run the benchmark then later on from your IDE. See, there is forks 0. That basically means the VM that started also executes the benchmark. Java GMH typically has this as the control VM, where all the results are calculated and everything is shown to you, and the measurement is done basically in the fork of the virtual machine. So the fork only runs your benchmark code, nothing else, and the results are communicated back. If you say fork 0, you can actually debug because the debug ends up in the same machine. You should not run benchmarks from your IDE for measurement. purposes, it will be mostly wrong. Trust me. So debug, yes. Everything else, no. Good. So coming back to our result. So we have here this nice little setup. We have a cheap edition, we have an expensive edition, and then we run our AO3A method and we get the same result. So the last one should be kind of expensive and the one above should be very cheap, but it's not. And then just for giggles, I disabled the compiler, the JIT compiler. It's the xint. And by using GVM args, you pass this parameter down to the fork. So it's not your main VM that runs it, it's just the fork that runs it. So we turn off compilation for our fork, and you suddenly see, oh, cheap is, oh, not cheap anymore, it's 220, and expensive is 450, 45. So kind of makes more sense. So more code, more expensive, cool, good. But it's still kind of odd that we have such really, really small numbers. So the first question is, can we actually measure time in a way that we can make sense out of it? So whom do you ask for time if you need time on your machine? Anyone? Java. What's your first go-to API to ask for time? System Nano? Anything else? Yeah, it's not that much more. It's nano time, it's time millis, time current millis. These are the two ones you can use. And if you do this, you ask an API. The API is basically your GVM. The GVM asks the operating system, and the operating system asks your hardware. And if you're lucky, the hardware doesn't ask anyone else. Nobody knows nowadays, but that should be the outcome. So we have nano time and we have current time millis. One important fact I'm always like to state, because it seems to kind of missed by most developers, nanotime is a time difference. So the time you get there is just a number. And it's guaranteed that the next reading is the same or larger. That's it. And it's, of course, in nanoseconds. And the right current time millis is a real time, so kind of your clock. That's the difference. On the left side, you never get actually any real time. You just get a relation between two measurements. That's it, the difference. And the right one is really time. Good. This means we can't actually measure less than a nanosecond. Right? But what can happen on a CPU right nowadays? So if you say we have a 3 gigahertz CPU, which is kind of what typical cloud machines are, we have a clock cycle that takes 0.33 nanoseconds. So 1 hertz is 0.33 nanoseconds long. If you know modern hardware, you know that it can run up to 6, even more instructions per cycle. So 1 hertz can give you 6 assembler instructions that are executed. So this means we can actually do a lot in 1 nanosecond. So it's about, if you're really, really running crappy code, it's 3 instructions maybe per nanosecond. And if you're lucky and the code is really, really cool, it could be 18 instructions per second. So we do a lot in less than a nanosecond, or in 1 nanosecond, but we can't measure it reliably. So what do we do? By the way, we can't even really measure a nanosecond. We can only measure 20 or 30 nanoseconds reliably. Why? Because your clock is code. Your clock is basically the same as you would write any other code. It's just time-based. It's just an API like any other, and it gives you something. So it needs time to do something. It has to go through them. It has to ask, it has to run code, it has to compile stuff, blah, blah, blah. So you measure code with code at the end of the day. So it doesn't really work, right? So here's a small benchmark. And once again, if you can execute this one, would be cool, because we can then compare numbers. This is from Alexei Shipilev. You find the GitHub link there. The timer resolution of your machine. So we run a benchmark. This is this nice piece here, where we say, okay, give me how long it takes to do nanotime. Just measure how long it takes to measure time. And this one is just kind of a one. When you see the full code, it's nothing else than a loop that produces a lot of measurements and prints them out later on. So if we execute this here on this machine right now, we'll say about 22 nanoseconds. This is how long it takes to call system nanotime. It's kind of odd. How do I know that it takes 22 nanoseconds when a call already takes 22 nanoseconds? Because I have to call it before and after, that would be already 44. And then the call in the middle, it's already kind of 60 nanoseconds from A to B. Okay. And if you just run this, you can see that each measurement increases the time, but the difference is kind of sometimes 20 nanoseconds, sometimes it's 30 nanoseconds. The difference is rarely anything like 21. It's mostly kind of something very constant. So that's really kind of difficult. And so at the end of the day, what we do is we don't measure time, we calculate it. How do you calculate time? Anyone? You could do this, would be a very elaborate version of it, but could be very difficult because it depends on the machine, how fast an instruction is, what kind of instruction you run. So it might not be the right one. I give you an idea. First of all, if you have time, execute this one and yell, please, how much resolution you see on your machine. Let's imagine you're standing next to the track and your stupid stopwatch can only do minutes. And your friend says, hey, I have a new beamer and I want to run, basically a couple of laps, please measure. And you say, so what do? Well, you basically say, hey, do 100 laps. Then you use your stopwatch and you do 209 minutes. And then you do a little bit of math and you get down to 2 minutes, 5 seconds, and 400 milliseconds. This is how we measure time with GMH. We have coarse execution measurement time, nanoseconds, which is not really nanoseconds, it's really, really coarse. But instead of executing it once, we execute it a lot of times, and then we just do an average. So we divide it and say, oh, this must be kind of give or take. Of course, one lap was kind of very fast and the other one was very slow. It's really an average. And this is what you get when you do benchmarks. There are differences where you can do things differently and you might get real numbers. But if you have a really, really small code that's really, really fast, that's as good as it gets. So if you measure something, you get 1.5 nanoseconds. And you're really proud of yourself, and then you tune something, you get 1.4, might be okay or might not be okay. This is really hard to tell if this really made a change, because it's all calculated. One kind of small fluctuation in all of the measurements will just basically blow your average. And you can repeat this 1,000 times, you might still end up with this code is actually slower than the other one. Yeah. This is how you would do it at the end of the day. But still, if there is, let's say, you save one instruction, and we already know that one instruction is 0.00 nanoseconds, something like that, still it's not very reliable to basically measure that you saved an instruction. And by the way, still, things we do might not become correct, and we'll see more of these examples later on. Good. By the way, we have a lot of clocks in our computer nowadays. These are just a few examples. There are more. Not every clock is enabled. And the last one, at least on the x86 architecture, is the so-called timestamp counter. That's a counter that runs within the CPU and will be increased with every hertz. It will adjust according to the scale of the machine, so you can reliably use this to determine things. If you don't have this one, low latency timestamp counter, you might get this. So for instance, this is HPEAT, the high performance event timer. I don't know why it's called high performance when it does this resolution, but I don't know, back in the days, and you get basically a latency of 1,100 nanoseconds. You can still do reliable benchmarks with this coarse latency. You just have to execute it often enough, and then you get down to a really, really nice average. So if you're a Linux guy, you can switch between time sources that are available on the fly on your machine. If you don't see TSC for your laptop, you might have a BIOS bug. Google. It's really sometimes really difficult to get TSC enabled. If you run a virtual machine, you often see the KVM clock coming up or something similar. This is the clock of the virtual machine, which might hopefully ask the OS underneath. It could also do other crazy things. You never know. So it becomes kind of a little unreliable at the end of the day. Good. We missed the topic. We discussed the 1 plus 1 at the end of the day. So let's do this. We have just made our code a little bit bigger at cheap 1, cheap 2, cheap 3, and something very expensive. And if we execute this, we see it's kind of almost the same all the time, except that number 3, where we use a long, uppercase long, is slower, which kind of is unexpected. And if you do an xint, and just basically disable the compiler, you can see that we get really, really different measurement results at the end of the day. So let's get to it. And what happens here is, and this is the first thing you have to learn, and something you might or might not have been exposed to before, dead code elimination by the VM. If the VM sees that your code is not used at all, it drops it during the compile. It might not drop it today, maybe not tomorrow, but definitely later. If code is not executed and there is no side effect, it will drop the code. So if you write really cool, lame code like this, where you don't see a single object, it will be dropped most of the time quite early in the game. The VM is capable of dropping loops, if conditions, exceptions, everything you don't need, boom, gone. And we will get to this later on because it might bite us. And I promised assembler code. Sorry. We have this add sheep and add sheep 3. One is time, which is a small long, and the other one is an object long. And let's look into the assembler code. And yes, this is something you probably won't see again today in any other talk. Assembler code, so enjoy it. This is the method, add sheep 2. All of this code is this method you have just written, 1 plus 1, or in this case, 1 plus time. That's it. It's really that big. And this is not a single line is yours. Because here at this point, when we do this addition of 10 to the stack pointer, and by the way, I can't explain most of it. I just really know what's important. This is where your method now should turn up, or your code, and it doesn't. We just pop the pointer again, do some nuts other things, and then we return here. So there is no code visible that's yours. Dead, gone. We already know that the long one, the long object, is kind of slower. So it seems to do more. And if we look at the right side, we see that we add something to our stack pointer. That's the entry point. And right above this, we can see a call to BD3, which is about here. And if you look there, it says invoke virtual long value. So we call the long value method at our long object. But there is no addition of time of 1 to this value. So we're not doing any addition. We call this long value, but we're not using it. So this is completely gone. So this part is here, that's cool, but the other part is completely gone. And the rest is really a ceremony just to get a method called. And please keep this in mind, because later on we talk about inlining, how to get rid of all this shit. Okay, so make us do stuff. Just trick the compiler in believing that your code is actually code that is worth executing. So by returning the code from the benchmark method, the benchmark framework, important, the framework does this for you, makes sure that the VM believes that this code is actually important. So it will use this and then just do something stupid with it. So it can't be de-optimized, or optimized in this case. So when you run this, you can actually see cheap 1, cheap 2, 3, and at expensive now have different runtimes as we would expect. Cheap is really cheap. Cheap 2 does something. Cheap 3 with an object is even slower, and then or a huge 3 times multiplications and division is really, really slow. Cool, good. So let's take another look. This is the code that does actually your addition to your time. So we move 1 to a register, that's our 1 plus, and then we do add the plus. This is the memory position here. So, and we add this to the AX, and that's it. That's all your code. These 2 lines is your code, the rest is VM overhead. Not actually VM overhead, it's kind of conceptual overhead at the end of the day. And on the right side, we do the same, but we do this with our long value. Looks slightly different, but because we have to do the long value call first, and we do some huge calculations of the memory address here, and that's it. So on the right one, you actually see that it takes 4 instructions. On the left side, it takes 2 instructions plus the long value overhead. So just by using the long value, you already see that there is a certain overhead involved when you actually use an object. Even so, you're not creating one, you're just accessing it. Good. So now we made sure that nothing is dropped from what we do. There's another way promoted by GMH, and it's called black holing. GMH does already black holing for us when we do a return. It just basically takes this one and sinks it into one of these black holes, and the black holes are written in a way that the VM can't drop the code. And because GMH is written by Alexei, and Alexei is writing some of the JIT compiler, he knows what to do to actually convince his own compiler to not drop it. And therefore, consume is shaped in a way to really trick the compiler in not doing anything. So we now see that expensive is finally expensive enough. Good, okay. So just by the way, because you might have wondered how expensive is at the end of the day, this is your expensive code. On the left side, this is the first compile of the C1. On the right side is the second compile of the C2. This is all it takes to do this times time divided by plus something stuff. So, by the way, good thing, second time AI today, you can drop this into Gemini. I did this yesterday and say, okay, explain me assembler. It does really a nice explanation what this code actually does. Because the opcodes are sometimes really hard to get for x86. So just drop this, including addresses, just free drop this and say, hey, explain me this assembler code. And you get a decent explanation. The other way around might not work. Good. So we are still doing dangerous things. So for instance, I said return what you do. The thing is, you should return everything you do, not just half of it. So good example here, this is our baseline where we do a single computation. It's kind of here, the pi whatever, just ignore it, it's just computing stuff on the CPU. When we do it wrong, we just basically call it twice, but only the second value is returned. Or, sorry, what? How could that happen? Should play some music. Here we go. So this one consumes both, and this one also just basically consumes the second in the black hole, and the first one is untouched. Here's the proof. If you run your baseline, you get 12 nanoseconds. And we can actually do some magic, I would say. You get 12 nanoseconds. If you measure wrong, you get also 12 nanoseconds. So it's actually really proving that we dropped 1/2 of the calculation. If we do a measurement right return, so we add both together, we get 24, twice as much, makes sense. And then of course we have 2 black holes, it's 25. It's important, a black hole is not free. So a return already uses a black hole. If you don't have a return and you black hole yourself, you have 1. If you use 2, there's a slight overhead, because black holing actually means consuming the data. And this means the CPU has to do some slight work, otherwise the compiler says, nah, right? So there's always an overhead. So don't clutter your code with consumes. That might be incorrect benchmark code at the end of the day anyway. So, good. And let's probe the JIP once again. We just run our code from A04B, what you have seen before. And now we can see that our JIP once again starts kind of fast and then drops slow. So, what the heck? And now let's try something else. Benchmarking. You can define for each method how often you want to do warm-up and how often do you want a measurement. So we have 3 times 1 second, 5 times 2 seconds, 10 times 1. Let's execute this and come up with this. So here on this side, we can actually see when we do our short version of the addition, it's 0.3. If we do the other one, it's 0.5. And this is only executing this single method. You can define, execute only the single method. Now I run basically both together at the end here, and I get something totally different. So something is really wrong with our benchmarks. You can see that what we get is not what we expect, what we should get. Okay. So and we just use the power of the tooling again, and you just basically convince your GDK to tell you when something is compiled. And as you can see here is the top one. When we compile it that way, we stay fast with 0.37 nanoseconds. And if we compile it the other way, we get slower with 0.4, 0.5. And we don't know why, and we can't influence it. The GDK is asynchronous. It decides on its own when it will compile and how it will compile. You can define that you don't want a background compile, stuff like that, but it just kind of changes this thing here a little bit and there a little bit. You will always be hit by certain things when you run your benchmark code. If you run it 3 times, you might already get 3 versions of your compiled code at the end of the day. It is not absolutely stable. It might not apply to you in production. I applied once to me in production when basically code that typically runs 5 minutes suddenly ran 12 or 13 every kind of 15th compilation. So this can be a real problem, but it's really hard to diagnose. But here you're already kind of hit by it small scale. What you can do is, and you probably remember our huge method, right? So all this stuff that was going on. At the end of the day, we want to get rid of it because just to execute this little code, we have to run this method overhead. Just we don't. And therefore, there's something that's called inlining. So the GDK and every kind of other language like C does it and the Graal compiler does it, is trying to prevent you from really calling a method. If the method is really small, the compiler decides to take the code that's in the method and copy it over to where it has been called from. So your ceremony will not run. It's just basically this small code will be copied over and then it takes care of the right registers and memory addresses. So it applies only to small methods, not the big ones. And this can only be applied to a certain level of inclusion. So if you call methods several times in other methods, so there's a certain call stack and then it stops basically inlining. We can disable inlining. By default, it's on. And you can just basically apply this and you will globally for the entire VM disable inlining and you can see the huge difference it makes when running the code. Yeah. I don't know. I have to check the assembler code at the end of the day. It probably might have. It might not even inline. It might directly copy the value without doing it. Okay, we'll see. But definitely what we can see here is that this is inlining and there's what we call compiler control and the GDK gives you the, not the GDK, GMH gives you the control over the compiler options. You can mark a method and say don't inline this one or force inlining if you want to have this. This is not available in the normal GDK. This is not an option you can use for your daily work and apply this freely to all the methods you have. It doesn't work. It's really just GMH. And you can either disable inlining completely or enable it completely by default, Or you can do compiler control. And as you can see here, as soon as we say, please call me, don't inline me, it's 1.6 nanoseconds. So the overhead of calling a method is about 1.5, 1.4, 2, depending on your machine, 3 nanoseconds. Golden rule, keep this in mind. If you call a method and it's not inlined, it's probably between 1.5 and 3 nanoseconds overhead. So if you call a huge method really, really a lot, there is something you can do about this. And then you have to attend the 1BRC tuning session that will be tomorrow. And they will talk about why they change code to make it inlineable and basically avoid this overhead. So if you call things a million times, you can already measure the difference kind of easily. Good. And expensive is already kind of, it's also inline, so it's 4 point something. But if you uninline it, it's about 5 nanoseconds. You can basically see the overhead. And by the way, because we'll get to you in 2 minutes, because we can, and I will show you why, we can run more than one instructions at a time. This is not easy to calculate. So you can't say, okay, when I do this plus this, it's now twice as much. It's not true, because the CPU is parallel in itself. Every code you write, even if it's single-threaded, will be executed in a parallel fashion. Therefore, it becomes really hard to do simple assumptions about, oh, I add one additional method, it might be that much longer, it might not be, because the CPU can do things in parallel and might be able to optimize things like hell. There is, I have to look this up, there is a nesting deepness that's defined. And if you're too deep, you will only the end will be inlined. The top of the stack won't be inlined. It will be inlined here, really at the end of your call stack. And it might uninline things if suddenly things get bigger and bigger. It just drops it again and makes it bigger. So this is an optimization process that continuously runs. Okay. This is one of the things that makes your code fast. If you don't inline, things are really, really slow. That's the biggest gain you can get. But you can also horribly make things wrong by just doing incorrect benchmarks. So never trust this first result, the golden rule. We have seen one thing, the 1 + 1 is always kind of really, really fast. This is something the GDK drops by default because Java C already evaluates this because it sees two constants and can do basically a simple math upfront. So it will never end up in your code. So if you really write something like 5 divided by sing, ba, 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 and all numbers, it will be evaluated upfront. The GDK drops code. So you might lose some of your benchmark codes by accident and then think at the end, oh, this is really, really fast. It's not. The JIT is not predictable. The JIT might really, really work against you at the end of the day, even so it's the king of the GVM at the end of the day in terms of performance. So always return all results or black hole them. Inlining makes a difference, and we have seen that warming also makes a difference already. Okay, good. So let's detour a little bit to setup. We already talked about data and already talked about before, which is here in this case setup. So before you run your some classic, GMH enables you to do a data setup. Not one, you can do many if you like. And you can do 3 different types of data setups. One that's called per iteration. An iteration here is really one of these measurements you have seen. One warm-up round, one measurement round. This is called an iteration. So that could be 1 second long, for instance. We do data setup before, then we call it as often as possible within this second. We calculate the result, we're cool. You can also say, do a trial, and this is the default if you don't define it. Trial means the entire test. So when we start our benchmark, it will be executed once, and then your entire benchmark runs. Never again. Or you can do invocation. And invocation means you call it before the method is called. So you basically do it, you call the method, do it, call the method, do it. And as we already know, we can't measure really precisely nanoseconds. So on the left, it's always the same code. On the left, we do trial, iteration-based, And on the right side, we do invocation-based. The problem is that this invocation becomes part of the measurement. So your setup is now part of the result. That's unavoidable because this is how a GMH works. Because the measurement is really difficult in nanoseconds, so we basically do 2 measurements only and run the loop here. We also do the setup here outside or inside of the measurement, and therefore it's part of it. You don't have to care if, let's say, your measurement runs for 5 milliseconds and your setup code runs for 10 nanoseconds. Just doesn't matter. So if the relations between time here and there is really huge, you can do this if necessary. You can do really, really nifty tricks with the state, because GMH gives you the ability to have dynamic state. So you can actually say, okay, give me a list of parameters for size, and then GMH will automatically say 1 trial with 1 trial with 10, 1 with 100, everything you defined here, and it will just repeat this over and over again. So you can easily scale your test in any dimensions. You can also have a setup of 2, 3, 5, 4, 7 states if you like. Then, of course, it will multiply itself into all dimensions, and then the benchmark will run forever. But you can easily see here that you can just run the benchmark and scale and see what might happen if you run a classic loop or if you run a stream on a defined set of data. The data might be 1 field, might be 10, might be 100, and then you can actually see the scale of your work. And the odd thing is that if you have 10 entries, that it doesn't take 10 times what it takes for 1. And if you say 100, it's not even close to what you would expect. So it's kind of odd at the end of the day when you see how the CPU works. So if you scale up and you want to do more, it's not the time relation you expect. And this is once again the magic that's running inside the JIT compiler and the magic that happens on your CPU. If we would have had this talk, let's say 25 years ago, this would be absolutely linear. The CPUs were kind of really simple. They were kind of non-concurrent, 1 instruction at a time at a hertz. That's it. You basically see really, really linear scale, but this is all gone. Now memory is slow, CPUs are fast, CPUs do a lot of things at the same time. Therefore, you get this kind of strange behavior. And here's the big warning. When you do benchmarks, give yourself enough data that makes actually sense at the end of the day. Otherwise, you end up with something like claiming, oh yeah, the more data we have, the faster it gets. Because 100 is 7 nanoseconds, 1 is 1 nanosecond. So let me make things always bigger because it will be faster. Doesn't make any sense. You have to understand what's going on behind the scenes. The interesting part here is, for our stream, it's quite the opposite. We get the same measurements, then it becomes a little slower, and then it seems to scale absolutely linearly, right? If times 10, you always basically increase the runtime by about the factor of 10. Here it starts to do almost the same, not exactly, but up to this point, it's really, really kind of odd, because there is no scale you would expect in these measurements at all. Okay, because only a few people have brought notebooks, let's just skip this. So what's wrong here with this kind of odd scale at the end of otherwise, we just revisit our topic here. This is a small task for you. What is wrong with this benchmark? Just based on what we just talked before. Sorry for this test. It's like in school, right? Just suddenly there's a test.
You're initializing the data before the size has been set. So you're probably getting exactly the same array list for every test.
I think the idea is right, but it's not exactly what happens. Anyone else?
Yeah, are you just testing the different caching levels in the hardware?
We will get to this in a second. It's not a problem,
Every time sorter is behaving differently because it depends by the different sorter.
right? Remember, setup is by default for the trial. And so we have a list with random elements, let's say 1 to something. And then we run our benchmark method once, and it runs on actually our field or list, your array list. And it will be sorted. And it will be executed again against the already sorted one, and again, again. So only the first execution is ever on the unsorted one, and everything else is basically going against the sorted one. So you betray yourself by accidentally having test data messed up in the first place. Of course, the functional programmers now say, oh, immutability to rescue. Yes, of course, but at the end of the day, immutability also means slower, and we are doing microbenchmarks here. So this might be a different thing. So yeah, the problem is really we set it only up once, and then we sort directly the data, so it becomes sorted after the first execution, and everything we measure on the right side is absolute garbage. But it looks nice. And this is the problem with benchmarks. They always look nice, and they seem to make sense. At the end of the day, you might not have measured anything. Okay. Let's keep an eye on the time. Yeah, good. So we can do certain things, and we can also just diagnose certain things. And when we diagnose, first thing is the environment. And as I basically mentioned in the beginning, it's really important what kind of environment you have, and it's important that you can change the environment quickly, and GMH can. So here in this case, we just basically switch to GDK and run the test again. And we have the famous system copy against manual copy battle of medium.com. And so we will battle this out now. And basically, as a bonus, there's an array copy going on as well. Good. So, GDK11. GDK11, we can see manual copy is slow. System copy and array copy are faster. GDK17, the same. Numbers slightly different. GDK19, okay. Seems to be matching. GDK20, suddenly system copy and array copy are way faster, which is really, really nice. And then GDK21 is kind of different, but they're getting closer together. So, different GDK, different results. And by the way, different GDK. So if you run this with Graal, you get a surprise. Your manual code is really, really slow, and the rest is kind of slower a little too. Even so, these are intrinsics, but it's not what you get. By the way, to be fair, this is not really latest Graal. It might have changed, but this was at the point in time when I created all of this. GDK11 was basically, GDK17 was the guy, the go-to guy, and GDK21 I just added 3 days ago. Okay, so here in this case, we know, okay, we should do system copy and array copy. They are slightly faster than our manual copy. Remember the beginning where the data was kind of totally different? Okay, so let's change the hardware. What we do here is, we have GDK21 on this little guy here. As you can see here, 146, 131, cool. And then we go to our Hetzner machine, and this is an AMD EPIC. And suddenly our manual code becomes way faster, and system copy is slowest. Bah. Nobody is right ever. Okay, let's do this again. And run the same code again and again on the Hetzner machine. As you can see here, it changes all the time. So this is not really helpful, right? We can't make a decision based on what we currently created, so it must be something we do incorrectly. Okay, let's try it again and just measure more often. So I increase the measurement and warm-up time and get to this. As you can see here, because we measure slightly differently, in the beginning, we have here warm-up rounds, 5 with 1 second, 10 measurement rounds with 1 second. We do 5, 1, and 10, 1 here, and 3 forks. And you always get to certain different results. So this is my local machine. It's slightly slower nowadays, kind of odd. And then you can see that our benchmark machine still gives us kind of odd results. So here, system copy is really, really slow. Here, system copy is really, really fast. Not really, really fast, right? The difference is that we would say it doesn't prove the point. So let's change our data dimensions. And we already learned we can do parameters quickly. We don't have to do anything else. And let's run this based on way more data. So we compare a small array of 10, 19, 11, and 12. So our manual code is slower. Then we do 1,000 entries and 100,000 entries. And you can see on my small little machine here, even so it's an AMD, manual copy really, really is slow at the end of the day compared to system copy. But if we do the same exercise on the big machine, you can see that suddenly manual copy wins. The more data it has, the faster it gets. That's still not helpful. I just want to basically prove a point, but I can't because everything moves. And this is what happens with benchmarks. Everything moves, and people basically want to go to bed and say, this is now the result, and just write it down and publish it on medium.com, and then you get what you get. Good, so let's change the data type. So instead of doing a byte array, I do a long, which basically gives me way more data, and we just battle it out again. It takes longer, and now we can see that our manual copy doesn't win anymore. Here they're kind of a little bit closer together. Here it's kind of blurry. It's kind of 10% difference only. But here you can see that a manual copy is now slow. So going from byte to long changes things big time. Even so, before we increased the amount of data and manual copy basically prevailed and was faster, now we changed data even more and we get absolutely the opposite. This is tiresome. Okay. You know, if you hate Java, now it's time to say it must be garbage collection, right? That's the first thing you get when someone talks Java and doesn't really like Java, or it's Java. It's always kind of. So let's ask the garbage collector. You can do this by the built-in profiler called prof.gc. You can always start this. It's always part of it, the distribution, so you don't have to install anything. And we basically see, okay, manually copy does per copy round 8,000 bytes per operation. So an operation is basically one execution of my method. It's 8K, 8K, 8K. So doesn't matter what we do, system copy, array copy, manual copy, it's always the same amount of memory we require to do one of these rounds. Okay. So what else? Then let's give them way more memory and just still look at what happens. Still, we do only 8K. We still see that here the result is 344. This is 46. Now the result is a little bit better. But it's just faster. It's not really giving us any kind of different vibe. Okay, so more memory definitely does something, but maybe not what we wanted to do. Next one is, just Google and say, my code is too slow. Second response will definitely be, you have to change the garbage collector. You have to tune your garbage collector, I promise you. So let's do this, and we change the garbage collector. We go back to our old serial GC from G1. As you can see here, 340, 380, almost 400. Still manual copy wins, and this should not be, right? Because we know this should not be. So let's go to ZGC. Okay. This is slightly disappointing. With ZGC, everything gets slower. Does anyone know why? I know ZGC is not really bad, but in this case,
I think it requires more structures and more memory to do its job, so you pay a little bit more upfront, but you get more predictable.
yes, but it doesn't really. We have later an example where we really see it requires more memory, but in this case it doesn't. But what happens is that ZGC, to really make the pauses small, gives the burden of garbage collection back to the thread that actually created the garbage. So you, as a thread, typically you stop, someone does the cleanup, and then you continue to run. You no longer have this luxury. You almost don't stop at all, but someone gives you a sign that you have to do some cleanup yourself. And just read about GC and how it does it. It basically moves some of the cleanup data to you, and you basically see suddenly, oh, I have to do this instead of that, and you take a short detour, and that's it. So it might be this. It's just guessing, because it gives basically memory cleanup control back to the thread who created the garbage. Okay, then let's try something else. So far, what we did was create always 8K garbage per invocation. Let's change this and copy really just from source to destination and reuse this. Instead of creating a new array, therefore array copy had to be eliminated, we do this again. And we can see manual copy and system copy initially with allocation and now without allocation. Boo, that's the difference. So what we see here is what we have done so far. We have not measured our code. What we actually have measured is garbage collector performance. The entire exercise so far was garbage collector performance measurements. So what we measured is how fast we can allocate memory and how fast we can release memory. That's what we did. Because now when we don't, we have a completely different result, which is way, way faster. We dropped about 300 nanoseconds. We can still see that manual copy is faster. But we can also say that we so far kind of benchmarked slightly incorrectly, at least for what we wanted to do. Okay. And then let's think about what we typically do when we copy. We often don't copy the entire array from A to B. We use it as a buffer, and when we use it as a buffer, we often copy the end to the beginning or the beginning to the end, so kind of. This is what we have done here. So instead of saying we copy from A to B, we copy from the end of A to the beginning of A, just half of the array up front. Will this change things significantly? Guess, please. I don't have any presence for right responses.
It'll probably change if the data size is small enough to fit on a cache line, as opposed to if you have to go and fetch it somewhere.
I know it's a lot of data, but as you can see here, we just talk about manual copy. Remember, manual copy, the entire array was 68 nanoseconds before. It's now 120 nanoseconds for half the array. And system copy is now 40 nanoseconds. It was about 70 or 80 nanoseconds before. It's now half the time. So our manual code is basically just half as fast, and system copy is twice as fast. It's kind of system copy fulfills our expectations. Doing half the work is half the time, but our code basically is now really slow because we just do half of it.
You haven't been able to optimize out the array length checks when you're using part of the array, and pos is a variable.
Yeah. Yeah, we have a second variable we have to run, or we have to do a calculation. That might be the reason. Okay. So, but let's say you have to gut work and say your Jira ticket, just to bring up this word again, your Jira ticket says, please benchmark the slow copy of A to B in our production code. So far, you basically said, okay, we have to get rid of system array copy because manual copying is faster. You do this, and actually, at the end of the day, your performance in production is quite the opposite because you haven't checked what production is actually doing. You're not copying from A to B, you're copying within A. And this gives us totally different results. Good. And by the way, we just have another, let's say, animal to kill. I think, no, this is not what you should say. But so there is something that's going on within the GVM. It's called loop optimization or loop unrolling. So the code we have written so far, this here, is perfect for what we call loop unrolling. So a loop is basically You get in, you increase a variable, you do your code, you jump back to the beginning, you do an if your variable is blah, 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 you increase it again, and so on and so on. Or quite the opposite defense. So you always have a jump, you always have an if to see if you reach the end. What computers don't like, or CPUs especially, jumps, evil, ifs, evil. These are two things your CPU doesn't like. And so what Java tries to do, and also C and all the other compilers, is we need less ifs and more doing. So the inner part is important. So we roll out, we unroll the loop. So instead of doing check, run code, back again, we basically check, do 4 operations at once, and then jump back to the beginning. Because we actually know the size of the array, and we can then basically do increases by 4 instead of by 1. And then if we have something that's kind of an array that's just 3 fields short, we do the rest at the end of the day. So we can unroll stuff, and this will be done automatically by the compiler. And if you can see here, when we say manual copy is 68, and then we try to break the unrolling, and we were successful, we get to 380. So most of the performance of your manually copy operation so far was due to unrolling, due to an optimization the VM was doing. And system copy, by the way, is kind of perfect all the time because it's an intrinsic. That's assembler code that exists right from the beginning. Nobody will ever touch this. That's kind of optimal instruction set already. So it basically stays within its parameters. And please don't ask me why this first one is 100 milliseconds, or 100 nano, and then later on gets back to 74. We have a couple of different ways of breaking the loop unrolling. One is we can use a long, because Java doesn't like long for a loop stride variable. We can actually do an increment that's not known. So if you have a known increment, let's say 1, 2, 3, 4, 5, Java can unroll. If you have one that's undefined, Java can't. And the same here, I just basically do this as a local store first, and then continue from there. And the interesting one is, I have no clue why, the local store in a variable first is way slower than just the opposite going for the field. It's one of these things where you say, it doesn't make sense at all, right? And this is what I wanted to preach today, is your benchmarks in most cases don't make any sense, because there are so many tricks and so many optimizations going on that your small benchmark, when you run it, might be totally wrong. You have to really go into the details, really understand what's going on there to make things fly. And by the way, I can unroll code this way. So I'm basically doing what a compiler would do otherwise for me. And you can see if I do an unroll manually, I'm back to 480 coming from this 715. So this one and that one. So you can optimize, but you don't get to the speed that has actually been designed into this. Okay, that would be cool if this would be really what happens at the end of the day. And here we can always kind of look into the compiler once again, because I basically said, this 68 is cool, but this 16,000 is kind of odd. And so basically say, C2 compiler, stop, and I basically say run only C1. And what I get is almost the same runtime for everything I've done before. So you can see that this loop optimization, this unrolling of the loop done by the C2 compiler is what brings us all the performance in the first place. But this also brings us this kind of odd behavior at the end of the day, because it's just not what it should be at the end of the day. Good. So I think it's a good time for a break. What would you say, 50 minutes, okay? Then you have more time at the end. Okay, 50 minutes, so we will meet again at 15:15, so you get 20 minutes. Thank you very much. If you have questions, please just come up and we go into details. Thank you. So So, okay. Thank you for coming back. I think we lost a couple of people, but it's fine. So let's go to memory and caches. You brought up this topic several times before. And by the way, I have to slightly speed up things because I have way too much content. Okay, first thing here is once again a loop. And you know loops are dangerous, therefore we like them. And so we stay with loops for a moment. What we do is we have a loop over 100,000 integers. And we just take a look and sum up all the content. Or in the method step 20, and this might actually has been working before. Hey, do you see that? Excellent. So step 20 does the same, but we have basically a counter of 20, so we do only every 20th element. And then we have here one that's, you can ignore as a variable size. Good. So what do you think? How much will we lose if we do steps by 20? Or how much do we will gain? Is it 20 times faster? Should be, right? It's just 20 times the data. 20 times faster? 1? 10 times faster? Not faster at all? Good. So these are the results. As you can see, is 27,000 for the full one. If we do half of this, it's 13,000, so it's basically really half of it. But if we do 20, it's a tenth. So we basically lost 50% of performance. Oh, that's odd, isn't it? And then we have, just for giggles, our unrolled loops, and just because to continue on the topic we had before. So something is wrong, right? Isn't it? Because we actually see that every 20th element is not as fast as we would do every 10th or something like that. So it's kind of odd. And when you watch the GMH doing its magic, you can see we start with kind of odd numbers, and then we get to a really nice one. And this is for our unrolled loop. We learned before that an unrolled loop should be always kind of slower, but here in this case, it's not. So it's just kind of jittery for a while, and then, ooh, everything is cool. It's unexpected, isn't it? Good. So why are things so complicated? Now we're getting down to the hardware. I promised hardware stuff, and now we are at hardware stuff. If you use prof perf norm, and this only works if you have an instrumented kernel with the perf extension. I don't even know if this works on Macs, but definitely works on the Linux guys, but not on every cloud machine because some of them don't give access to the low-level details. So the best is you have real hardware without the abstraction layers. So we can see when we use the perf norm, the program gets slower, so there's an overhead involved in measuring things. We can see that we do 1.2 instructions per cycle. Remember when I said we can do up to 6 instructions per cycle on a modern CPU? This doesn't seem to be the case here. We can see that we do loads from the L1 cache, and so on and so on. So here our instructions, our cycles. Okay. And then this is the other one where we actually run step 20. As you can see here, it's a tenth. This works, but only half of the instructions per cycle. We don't even do 1 instructions per cycle. So we're basically just halting mostly the CPU all the time. And if you can see here, as we do cache loads, but as many cache loads as we do misses. So every cache load is a cache miss. We are not finding our data in the cache. While on this side, we are basically finding our data because it's 83,000 hits or uses and only 5,300 are misses. So we are basically missing the cache a lot. And the same you can see here on this is stalled front-end cycles. The problem is with these data. If this is an AMD CPU, you get this. If this is an Intel CPU, you get that. The output of perf is kind of not standardized. Some CPUs give you this data, some don't. So it's really hard to read. In this case, it's relatively clear. We can here basically see the load misses, and that's it. The AMD guys don't give you caches beyond. You have to use special parameters to maybe access something like the L2, L3 cache hits. They typically ononly give you LLCs, or kind of lower level caches. I don't say which one. So it's really kind of a little bit complicated. But you can see is we miss the cache. So this is the reason why we are slow. We are missing our caches. And this is actually how a computer nowadays works. Left, this is what we Java developers are used to. We have a thread, we have a stack, we have a heap, period, is a JVM. But the computer on the right side is actually a core where we do computation. Then we have registers, the smallest memory pieces you can imagine. We have L1 cache, L2 cache, L3 cache. Some have even L4 caches. Some of them are across core, some of them are for one core. Then you have your main memory, you have your virtual memory, and then this is your entire computer. So it's really kind of complicated. And therefore, it's always kind of interesting to know how much it actually costs to go there. But this is something we will evaluate quickly in a second. So we have another one of these interesting copy examples. So we have, in this case, I have to check what I actually have here. We have two arrays, a source and a destination array, which holds other arrays, so arrays of arrays. And what we do is, instead of using always the same input array, we have a huge volume of arrays. So we have sometimes 1, sometimes 10, and sometimes 10,000. And before we do our copy here, we actually get us randomly one of these many. So if we have only set up one, we're basically hitting the cache all the time because we get all the time the same. Other than that, we get different ones. And as you can see here, is when we run our code, we get slower the more of these random arrays we have. So we have a lot of data. And the more we have, the more unstructured we access it, the slower it gets. Okay, but it's not really as slow as we would imagine in the first place. So let's make this even bigger. And by the way, I'm using kind of some of the BRC examples here. So what we do is, and this is very elaborate code, is we have two data arrays. One is our data, one is garbage. So we are not accessing it, but we're creating it. I have a flag that basically says me, okay, I want to have a test case with garbage and one without garbage, and one where we have random data, and sometimes we have linear data. And so we just want to basically see what the CPU does with us. And this is what comes out of it. I'm sorry, this might be a little bit difficult to read. So when we do our parsing of the data, and so basically I use a city, semicolon, temperature, I'm looking for the semicolon. This is what we do. Nothing else. If I have basically here, I have not extra garbage and I have not created any random structure, so everything is linear, it's 57,000 nanoseconds. When I have created extra garbage and I have random, it's 81,000, and then everything is in between. So you can see is the more kind of data I have floating around, even so I don't touch it, and the more unstructured my data is by shoveling it. So when you create basically, let's say you fill things initially here, where you just create a new byte array. It's in memory, new byte array, new byte array, new byte array. Sure, it's linear. What we do is new byte array, we will use this one, fill it up with ones we don't use. We use this one, fill it up with things we don't use, but keep them so they're never garbage collected. And so we get basically a structure that's very kind of memory filled up and very random. You can see the more random you are, the worse the runtime is at the end of the day. And you can actually see this in the behavior of your output. So here you have basically the warm-up as well as the measurement is always the same time. It's really kind of steady. Both is false. The same for the big data set. Here it gets a little bit kind of nervous. So this is kind of odd. The rest might be okay. On the right side, you can see false but random data. So we have basically an access that's not linear. You can see the runtime has increased. Okay, but warm-up is the same. And then if we do the same here, you can actually see how erratic this is. And this is because we are not hitting the cache in a predictable way. So the CPU tries to kind of deal with its caches in a very predictive way. Say, okay, you touched this, you might touch this again, let's keep it here. Oh, you don't. Okay, give me that. Oh, last time you needed this time. Okay, and this is basically what you get at the end of the day. You get runtimes that are basically all over the place because you always miss the cache. This basically means you cannot really rely on the runtime in this case because it will be this erratic at the end of the day. Sometimes you hit the cache, sometimes you miss the cache, sometimes you do both. So it's very, very complicated at the end of the day. When we touch it differently, in this case, by saying, hey, this one basically says I always use, so we basically fill up the entire memory all the time. So before I basically said sometimes I fill it up, sometimes I don't. Here in this case, I have only one state. I fill up the entire memory with this data structure. And then here in this cache hit case, I use only the first one. And this one, basically I rotate to all the data. So basically this direction and beginning there. So no, not random. So always going one way. And this is the data I get. For the cache miss scenario, you see it's absolutely, no, not absolutely, but almost stable. So before I was basically sometimes hitting it, sometimes not, because it was random in my cache, in the memory. Now basically, because I'm always going forward and then basically starting on the other side, it's very predictable. And predictable here in this case means I'm always kind of a miss. So I'm not going back to data I might have touched before. Therefore, we get very predictable data. And the same here for cache hit. I'm always just accessing a small set of data. It's relatively stable, except here there's something odd going on. So you see that it's kind of weird, and especially the warm-up is different from the iterations once again. So here, the garbage digit compiler came up with something it later on decided is not worth keeping and goes absolutely into the wrong direction. No idea why, to be honest. So if we just look into the CPU again and see the cache misses, you can see here we have load cache misses and cache loads. On the other side where we hit, you can actually see here it's almost the same. It's odd. This doesn't really show what we have basically expected. That should be different. But you can see here we do more instructions per cycles than here. There is something else going on. Well, here in this case, you can see that we have something that's called stalled cycles front end. And this is where this difference between CPUs comes into play. These are the AMD guys, and the AMD guys are kind of here telling you that when we loaded our front end, so before we execute the code, we don't have the data we need for the code. So we basically, the cycle we wanted to start with our instruction has to wait because the code is not, the data is not there yet. So it's still living in memory and it's still transferred to us. And therefore we have these stalled front-end cycles. And this tells us that this code is very efficient and this is very inefficient. So it's really hard to read the data, but it's important when you want to do real benchmarks. And here is why things are so complicated. This is CPU, we learned it's about 0.4 nanoseconds per iteration. Not per iteration, per CPU cycle. If you have to get something from the cache, it's basically twice as much time. L1 cache. If you go to the L2 one, it's 2.8 nanoseconds. If you go to L3, it's almost 28 nanoseconds. So L3 is already kind of a very lame cache. If you have to go to memory, if you have to go to memory, it's 100 nanoseconds. And because we can't really think in nanoseconds that well, let's do this with seconds. So one CPU cycle is 1 second. L1 cache 2, L2 cache 3, 7, and L3 cache is 1 minute. So it takes 1 minute to get me data from L3 cache. And it takes 4 minutes to get me memory data. Therefore, if you do anything and you go to memory, it's always a wait. It's always a long wait. Any kind of data you fetch from memory, it's not in the cache, especially not in one of the L1 or L2s. It's always long runtime. And this is what happens during your benchmarks as well. As you provoke basically this behavior in a certain way, either you always run against the cache, which might not happen in production, or you don't, but in production you actually hit the cache. So this is one the really come up with good data and understand what's going on behind the scenes. By the way, all the guys who like microservices, going microservice-wise to San Francisco to New York is 5 years. A monolith is way faster than a microservice when you fetch data. This is important to keep in mind. Okay, good. This is our famous CPU, and I promised you to show to you this. So CPUs nowadays can do 5 to 7 instructions at one go, so a cycle for 1 hertz, because they have multiple execution units. And these execution units are basically here. I can do integer arithmetic, I can divisions, I can vector instructions, I can vector multiplications, blah, blah, blah. Not everything is there in the same order of magnitude. So some of them are kind of here. You have 4 integer addition calculation thingies, but you have only 1 or 2 for loading data here. So some of them are really, really there a lot, some of them not. When you get in with an instruction, the CPU will basically schedule it to be executed on one of these. If there's another instruction which doesn't rely on data from the other one, from the first one, it will be scheduled to be on the second one. If there's another one that's not depending on any data before, it will be scheduled for another slot. So if everything runs cool, your program runs basically 5 to 7 instructions in parallel without you doing any concurrent programming. This is how real concurrent programming works, because you don't have to. By the way, how does hyperthreading work? Does anyone know?
Yeah, you get separate ALUs, right, when you share that.
Hyperthreading is a way given by the CPU manufacturing to deal with your bad code, because most of your code is lame and does 1 instructions, 1.5 maybe, or 0.5 you have seen before. So all these units here, damn it, sorry. All these units here are stale most of the time. So what they do is they say, okay, let's create a virtual thread that uses these things. And this is a hyperthread. A hyperthread is nothing else than using these concurrent thingies at the same time. So you get a virtual representation of a core by utilizing what you are currently not using. This means when you have a well-tuned program that runs 5 instructions a second, your hyperthread can't run because there is nothing it can run on. It becomes a normal thread because it has to wait till the CPU is idle. It's one of the reasons why they might abandon hyperthreading in the long run. First of all, it's very hard to organize on a CPU, and it doesn't give you that much benefit as well, especially when you have well-tuned programs. Hyperthreading is really, really a problem at the end of the day. Only bad code runs good in hyperthreads. Right? If your code runs well in hyperthreads, it's bad code. Sorry. Good. So what we learned, GC, always different results. We might accidentally measure only allocation speed and not really what we wanted to do. Our loops are mostly unrolled, especially the primitive ones. The JIT is still unpredictable. Getting the right data arranged is really, really hard. If we do it incorrectly, we measure something that's not what we expect. Memory access is expensive. Cache is our friend info at the same time. And the CPU is highly concurrent. The last ones are really for tuning at the end of the day. If you really want to tune things, this is where you get most bucks for the bang. Good. Warm-up and measurement. So far, we always assumed our code would be hot. So we always have warm-up time, and the code is being executed a lot, and the JIT is basically doing all this stuff, and then we execute and we measure. But this might not be true. So if your server starts up, it might execute code only once. If your server stops, it might execute code only once. If, for instance, at night, your data stream is broken and you suddenly get a null pointer exception, you execute code you have never seen before the entire day. So this is one-time execution of code. Then, of course, which code calls me, how often, and also the entire hierarchy is important at the end of the day. This is something we are not touching today because it just fills another 45-minute call. So the warm-up thingy here is designed to bring our benchmark into a defined state. And we have seen the defined state might not be as defined as we think, but it's more defined than actually not doing it at all. So this is what we have done before. We can change how we do things. We can actually say, don't warm up at all. This is this one here, basically no warm up at all. a really short warm-up for just 10 milliseconds, a long one, and so on and so on. If we run the code now for our manually copy loop, you have seen the manual copy loop before, and our system array copy, a manual one is really, really slow. So if you have not warmed it up, it takes a horrible amount of time. As soon as you start to warm it up, it starts to gain speed. So warm is 4.6, and if it's really hot, so we basically trained it well, it's 1,700 nanoseconds. And the system copy here, the same. This hot one is odd, isn't it? It's basically slower than the cold and the warm one. Doesn't make any sense. Same here, warm is different from the others, and the same here. It's kind of almost expected. I would say this is the better one, but you can see here that things are kind of odd again. This one is totally different from these ones. So as you can see, warming my code is not easy. Having really cold code is easy for a benchmark, and really, really hot code is easy. Code that's lukewarm, right in the middle, it's difficult because sometimes it might be warm, sometimes it might be warmer, sometimes it might be just, you can feel this is not cold anymore, and therefore it's really, really hard to do any sensible benchmarks with rarely executed code. Benchmarks for not executed code or often executed code, that's easy, but right in the middle, that's damn difficult to do. By the way, here is the good example of what we have seen before, why suddenly our system copy was different. As you can see, once again, our JIT compiler decided for this run to do a lot, and for that run, only a few things. For this one, it's really, really fast. For this one, it's really, really slow. Same program, same execution, same VM, just executed a few seconds later. Not on the notebook, on the server machine. So as you can see, the JIT is unpredictable, and therefore it makes it hard for you to measure things. It might also hit you in production if you're lucky. Probably you're not lucky, which is good in this case. So cool. Okay. When we level the JIT power and basically say, okay, here in this case only do level 1, in this case don't do tiered compilation, already jump to C2, do all the upfront work, to forget about it, and don't do background compilation, so it's basically the full scale of parameters you can append to a VM to do nuts things. You can still see that kind of is a little bit more predictable, so the warm-up here is always kind of in the middle between cold and hot. But these ones here are kind of better. Hot is hot, warm is warm, but cold and warm are kind of, that's unsatisfying. So it doesn't help. So even if you play by the rules of the VM and say, okay, forbid background compilation, say C2 only, don't do any tiered compilation, you still get really, really hard to measure results. And obviously you are never disabling tiered compilation in production, or do you? Who has disabled tiered compilation in production? No? The thing is, when you see sometimes Docker containers for Java Spring Boot, you often see tiered compilation, disable tiered compilation, or tiered compilation stop at level 1. It's kind of someone said once, you have to do it that way, because otherwise the process is not gaining speed that fast. Okay, good. So, remember we said once in the beginning, never do streams and lambdas, period, right? And so we have written a benchmark, and the benchmark says a cold lambda is really, really slow, and the hot lambda is really, really fast. So just by warming, you can see what the difference is. It's huge. And here a loop, for instance, you can see that the warm one is kind of an outlier, and the hot one is kind of strange. So the stream isn't that bad, right? What we do right now is just this nonsense, if this is an even number, then sum it up, otherwise skip it. So if we now say, instead of doing this nuts, odd and even, and do a sum, we just keep things busy by doing integer, square roots, modulo, something that's really expensive. So if you need to burn CPU, do something with a big integer, it's very helpful to burn CPU. So as you can see here, if we burn CPU, we have something in this loop or in this stream that's consuming enough time. We don't care about warm-up. We don't care about cold loops, warm loops, loop streams at all. So if you have enough to do, the question is a stream bad should never come up. A stream is not bad, you just give it the wrong thing to do. Or you use it not often enough. So a stream that's only used once might not be a good idea. A stream that's used often is cool because it can be warmed quite nicely. Okay. So, and here the same with consume. There's a nice functionality within GMH that says, instead of writing your own big integer calculation to do nuts things, you can use black hole consume. There is a calculation that will never be de-optimized or optimized by the compiler, so it will never disappear, it will always be something. And the bigger the number, the longer it takes, but it's not defined how long it might take. So these 10,000 something might be a couple of nanoseconds or microseconds. It really depends what the CPU is doing with all of that. So once again, if you have something to do for your CPU, it doesn't matter if you run lambda streams or loops or something like that. It doesn't matter. And the same for your benchmark. When you think about the benchmark, what you do with the benchmark, try to do something that really is a production problem, that is really the challenge. Not trying to come up with, oh, you know, I have seen lambdas all over the place. Let's prove that lambdas are slower and then reprogram the entire code and make things faster. That's likely not your problem. Okay. So we can, by the way, also measure differently. We have different measurement types. One is called throughput. It's this one. One is called average time. This is the one we always used. Single shot and sample time. And just without getting into much details, what you can do is average time, what we have seen before, how much time for one operation. The throughput one is how many operations for how much time. So you can basically say, hey, I'm interested in milliseconds. You basically get 74 operations per millisecond. So it's the opposite, basically. It's up to you what you find easier to digest. I'm always kind of tending to what's bigger is slower. That's easier for the brain. And therefore, I'm always going with average time. And the sample one is trying to give you more insights how the execution worked. And so you can also see P95s, P90s, stuff like that. So you see if you have a lot of jitter or not. The bad thing with single shot is it's a single shot. And this single shot always has the invocation time in it as well. And it's always kind of without any warm-up. So it's kind of the do it once and see what happens. I haven't found a way to combine a warm-up that's average time with a single shot execution. Doesn't seem to be supported, but maybe I have to send a pull request. Okay, flow changes. This is kind of a nice program with a lot of integers as strings. So you basically have just always new string from I. So 1, 2, 3, 4, 5 as strings in this array. And once in a while, there is any or 42 in it. Any means you can't parse it, so you will get an exception. 42 says, I'm cool, I can still continue to be parsed. And here you actually have the code, integer value of integer, and then sometimes we have a number exception. In this case, we say it's 0. So if you run this code under normal circumstances with the always integers, the compiler will remove your exception block entirely. It will not be in the code at all. It will just basically be ignored, and it risks to run into an exception. And if this is the case, it will bring back the code and start over again. We can actually prove that. When we run our code, and we have basically set up something here that says, oh, here, benchmark parameters, and you can actually calculate where you are at the moment. So how many warm-up rounds do we have? 3 plus 6, 1, 2, 3, 4, 5, 6. In this case, do any, otherwise do 42. So for this one, for the 11th one, I basically created an exception case, and you see the runtime basically spikes for a short moment, and then it continues, but at a higher level. And this is what happens in your benchmark. You have this one-time event which says create code from scratch again. You get new code, and this code looks different than the code before. So if you, in reality, you have something that contains data that might be bogus, don't write a benchmark that has only good data, because you will never run into the exception blocks and the exception handling. The VM will drop your code, and it will not be there, and will be way faster. This is one of these. When you benchmark, try to benchmark with real data. Best would be with your unit test data. If your unit test data is bad, it's a different story. Okay, here is one that's kind of trying to prove a point. So number 6 has any and yes. So we basically have always the problem in our code. So it should never produce a different version. And so we can see it starts and then it runs at this level forever. So 11 is slightly different because we have to take a different path here. Even so, it's not part of the warm-up. We get a slight fluke, but the rest is really different. What you can see is this is 6,800 and the other one was 5,600, something like that. The initial code without the exception was way, way faster than the code with the exception right from the start. So your code and your data decides how your simulation runs. So keep this in mind. And here, I'm sorry for this source code. This is probably the one where the people complained the most last time when I presented. Quick one. We have a lot of arrays. One is sorted, just all the integers. One is unsorted. One has a pattern. So 1, 2, 1, 2, 1, 2. The other one has a pattern 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And the one is a shuffled pattern. I just take this data, copy it over, and randomize it. When we run our code here, it's just basically go over all the array. If there is a value bigger than 50 million, do a right shift, otherwise do a left shift and sum it up. By the way, this is important. If you put here and here the exact same code, your branch will disappear into a void. Because Java sees, hey, you're doing the same thing in all the cases. Why do you do the if? Skip the if. So this will be de-optimized or optimized in this case and will disappear. By the way, if this is something like an object access, you go into an object and you do certain things, it will not de-optimize because Java can't see if this thing in the object is basically having a side effect or not. So as soon as you have something with an object here, there is no way to de-optimize or to optimize it. It will always kind of be part of the story. So good. So we basically run with a pattern. So our huge array has elements less bigger than 50 million. And the other one, the pattern 5, is smaller, bigger, bigger. The random one is kind of big, small, small, and so on and so on. As you can see here, if you go over the data that's sorted, so the first half is smaller and the second half is bigger, you have the best runtime. Almost the best. Especially here, you can see it's the best one. On my notebook, on the Intel one. The AMD one has a different runtime behavior. If you have any kind of pattern, you'll get also good runtime. If you have unsorted or random data, you get really bad runtime. What bad runtime is basically twice as slow. Twice as slow? Half the speed. So what we have here is what is called branch prediction. So the CPU sees this branch and says, okay, I have execution units. I have to fill my execution units. Let me already start this thing, even so I don't know why, if this turns out to be true or false. So the CPU will branch predict and say, most likely this branch will take, and I will already start to execute. If this was wrong, it will discard everything and start over again and doing this. Because we can't predict with random and unsorted reliably, we always end up taking the wrong branch in most cases. If we can predict anything with 2, 5, and the sorted one, we really nicely can optimize this here and put this on the CPU in a very efficient way. what I wanted to say here is branches are bad for your code. If you need a branch in high-speed code, it works against your performance. Therefore, attend the 1BRC challenge tuning session tomorrow. I think the deep dive, they will show you how to write code without any ifs. And this is possible and might twist your brain a little bit. Okay. Here, just for giggles, this is the pattern 2. We can execute 4.7 instructions per cycle. If we have the random one, it's down to 3. And here, with the unsorted one, is down to 2.7. So you can see how slow we get because we always miss our branch at the end of the day. And here, and this is the complicated one, we don't have any branch misses here, and only branch misses here. So the data from the perf is not correct. You have to once again look at the stalled front-end cycles. This is low, this is high, this is high, this is low. This indicates, oh, you're missing the branch, you have to wait, you have to do some calculations, or you basically have to retire the operation you started and you have to do new things again.
But it says it doesn't have any branch misses because it just gives up and goes,
It always predicts. It always comes up with something. But it's just basically flip-flops the entire time. And it can actually really remember this for a long time. This is not what the CPU forgets. The prediction data is something the CPU remembers for a long time. Important one is the GDK. GVM also does branch prediction. It's kind of odd, isn't it? The C1 and C2 or C2 compiler actually counts which branch is taken, and the one is taken is lifted up. So basically, if the second one is taken all the time, it's copy up, and the other one is copy down. So basically, your entire branch is flipped. And vice versa. This can work against the CPU. So there are cases where the branch prediction from the GDK actually renders the CPU performance void because it came up with the wrong decision. But here, once again, data. It's all about data when you microbenchmark. Okay. Good. Time. We already talked about this. You can consume time. Once again, our stream and loop example. Just do something nuts here, something nuts there, with allocation, without allocation, and then you can consume time. And the odd thing is, I already showed you that slide, didn't I? It's kind of similar to what I already told you before. Okay, I have the same thing twice. Good, okay, forget about it. Sorry about. So, it's important when your code runs. If it's doing startup, if it's doing shutdown, if it's right in the middle at night when there's an exception, this makes a huge difference when you do a microbenchmark, because you might actually write code that's never running this way in production at all. Your simulation of warm-up code, so code that's sometimes executed, sometimes kind of middle tier warm, it's really hard. You can't really do this correctly because it depends on how often it's executed, depending on the CPU model and the CPU and the data and all the stuff. So it's really, really difficult. Once again, the JIT is unpredictable. Same thing. And I will actually ask Alexei tomorrow why this is also unpredictable. The program flow is key for your production data as well as for your test data. So if you don't have this, branch predictions, and then perf is a very nice tool, but not clear sometimes when you read the output. So you have to actually know what you're looking for to really get with the data forward. So we still have 35 minutes. This is cool. And now we can turn to threads. You might have just kind of waited for this for the entire time, hopefully. So what we can do here is independent workloads. And this is kind of an easy setup at the end of the day. So we have our benchmark, our setup as before, and then we have a benchmark routine, and this says thread 1. This means we run this routine one thread. And this one here will actually use 2 threads. So 2 threads run the same code in parallel. You can do it with 4, whatever you like. So you can just define how it should run. You can also define if you want to have two methods running at the same time, this thread, that thread, but in this case, we just basically do one method and just scale it up. So here we wrote a split. Just show you this again. So this is a split operation with a comma, similar to what the one BIC will show you. And you can see here, hey, one CPU, one thread, 11, 2, 3, 4. Well, this is kind of odd. So this one is already kind of slower, and this one is 8. And it should be all the same number at the end of the day, shouldn't it? Because of 8 real cores and 8 threads doing the same thing, all the operations should run the same. They don't. They're getting slower. Then, for your notebook, you can plug it in and plug it out. You can actually see that the performance will change. Doesn't apply to all the notebooks, but to some. And then let's do something else and try to turn off multi-threading and turn off the turbo mode, which actually is the scale up the CPU. And you can see here is something similar happens. It's not as pronounced as here, where it's basically twice the speed or half the speed. It's slightly different. And if you now turn off from battery power to performance, it's kind of what you would expect. So performance mode, no scaling, no hyper-threading, seems to give us, and of course plugged in, seems to give us what we are looking for. But it's odd, isn't it? It's kind of really annoying at the end of the day, and it's not really perfect. So let's diagnose things, and I will do this quick, otherwise we will spend the night here. So if we run our performance test with the famous prof GC, you will see that we allocate 4K per loop. So we're currently burning a lot of memory for one split iteration on our data. Same here, same there. Okay, good. You can see is the allocation rate per second about 3 megabytes or 3 gigabytes up to 13 gigabytes per second. It's really that fast. You can allocate in Java easily 13 gigabytes a second turnover, memory turnover. That's kind of easily doable. And most of you will probably do it and never noticed. Okay, let's do the same thing and just turn off the SMT and the turbo. So no hyper-threading, the data stays all the same. The only thing you see here, obviously, that the memory consumption per the allocation rate is lower. So this one is actually the same here. Okay, maybe this gives us a direction, maybe it doesn't. First one, Java haters, change the garbage collector. As you can see here, it stays the same. Use another garbage collector. This was G1, and this is serial. It stays the same. Okay. Throughput, yeah, slightly higher. So maybe serial GC is better than G1. Okay. G1, ZGC. And here we come to what you mentioned. ZGC allocates, for whatever reason, more memory for the same data churn. And this is probably of one of these 64-bit thingies, and this is an older version I'm currently using. So this is kind of already odd. Good, maybe there's something else. Let's use Shenandoah. Oh, Shenandoah is okay, fine. This seems to match what we expect. Okay, nothing so far. Yeah, but what about just getting rid of allocation overall? So right now we deal with split. A split is a very expensive operation. It creates a lot of memory because it always uses copies of the string. It uses always an array it creates and always returns this to you. So that's kind of, and if you look under the hood, it creates even array lists in between. So it's not really efficient. So let's do string tokenizer instead and run it. And as you can see here, runtime improves and it seems slightly better in scale. Okay. Let's do another one, turn off turbo, let's turn off hyper-threading, and suddenly you have linear scale. So more CPUs means power stays the same, but basically throughput increases. And as you can see here, what we have done before is we once again tested our memory allocation speed. We haven't tested our program code, we tested allocation speed. So the allocation was basically hindering us to gain speed. But of course, you might now ask, René, what about this SMT turbo thingy? Well, you know, at the end of the day, just to prove that we are not burning any memory right now, all cool. This, by the way, is a different story. So what happens here is, if your thingy here, and this really depends on your computer model, and probably it's a laptop, and a laptop has a limit, thermal power limit. So if you run one core, it probably runs, in this case, 4.4 gigahertz. If two cores are active, they still run 4.4, maybe 4.2 gigahertz. If four cores are active, they only run 3.3 gigahertz. So they all get throttled down. And if you have all 8 cores in use, it's 2.8 gigahertz. So because you burn a lot of power and this creates heat, the CPU protects itself and basically says, you know, that's way too much for my little thingy here. Let me just run things slower. So when you benchmark on your notebook, you actually are not benchmarking correctly because you don't have scale, linear scale, because your CPU are limited in terms of how much heat you can produce at the end of the day. It might be different for the Apple CPUs. I would really love to see if the ARMs basically do the same. But this is what actually happens on most of the normal older Intels. The newer ones might also be slightly different. So by disabling turbo mode and hyperthreading, I'm basically not running into this thermal problem, and so I basically get the same gigahertz speed all the time. Slower, but predictable. This happens also on cloud machines. If you go to Amazon or to Google and you say, give me an 8-core cloud machine, you're never, ever, unless you set a specific checkbox, get a real 8-core machine. You always get 4 real cores and 4 hyperthreads. Everything else is just what they give you. You really have to ask for real cores to get real cores. And the same with the turbo mode, depending on what kind of model they're running, you might even have a turbo mode in the data center. If the machine is idle, you're the only customer, you might actually get more gigahertz out of the CPU than when all the others are running on the same CPU at the same time. It really depends on the model. It really depends when you do it and how often you do it. So don't be surprised when you bring the same machine up tomorrow and the benchmark suddenly changes. You might just end up on a machine that is heavily occupied, even so your CPU is idle, but the rest might be kind of busy. You are just limited by the thermal power of the CPU at the end of the day. Good. By the way, you might just ask, René, you did new string tokenizer on the left side, right? New string tokenizer. Why are we not burning any memory? Well, what we do here is we once again use a feature of the GVM, and this means the JIT runs an escape analysis. So if this object, string tokenizer, is not used or returned outside of my method, it might be able to store this on the stack instead of on the heap. So heap means garbage collection, stack means no garbage collection. This is a very simple escape analysis, so it doesn't cover a lot of cases, but it helps in this case to completely run without any allocation of memory. Once again, this is important. If you on production do this, everything is cool. If you do in your test a field and put a string tokenizer there, you're not doing the same thing because suddenly there is no escape analysis possible anymore. So you change the entire setup and you come up with totally different running programs. So it's always important to see what you do in production and then come up with a benchmark. Good. So CPUs are all different. It's very important. Your laptop is not your benchmark friend.
Is it possible to specify the kind of thread that the JMH uses to run benchmarking, choosing between platform and virtual threads?
Nope, not that I know of. But of course, you can do your own thread pools and do nasty things, but I think the GMH documentation states you should try to avoid that because it might give you a false sense of measurement because you do your own synchronization against what the synchronization runs on GMH level. So it's kind of a difficult game. So in this case, it's always a real one. Yeah, but probably, if I know Alexei, there might be already a hidden switch to do this. I don't know. Good. Hyperthreading sucks, by the way, for benchmarking. It's really, really bad for production code. It might be okay, especially when you run a database as a backend. Your Spring Boot application doesn't care if you run it on a hyperthread or not. Core power limits you. There are memory allocation limits, so there is a certain amount of news you can do at the time. So it might be, in this case, what I just did here on this one, might be about 13 or 14 gigabytes a second I can allocate before I run out of bandwidth between memory and CPU. Because what happens, what Java does is if you say new, Java always initializes this piece of memory. So if you say new byte area of 1K, it goes there and writes to it. This basically means you need the bandwidth to actually move data back and forth. It's not just the new, it's really kind of write first. And this basically limits your throughput in terms of how much memory you can actually accumulate at the time. Immutability is, in this case, not your friend. Mutability is your friend in terms of performance, not in terms of correct code. Okay, so remember, in the beginning, I showed you the famous do string builder or else. And of course, I want to give you an answer at the end of the day. And this is the answer. So we have kind of 3 strings in an integer. We do a plain one, we do a concatenation, we get a builder sized, and we get a builder non-fluid. This is a fluid one where you just append, and this is a non-fluid one. Will there be any runtime difference between this version and that version? Probably not, okay. Here we go. So if we use a normal builder, it's 8 nanoseconds. The non-fluid version is 21 nanoseconds. The thing is, the GDK or the GVM discovers your common usage patterns. They know that you typically say .append, and they can optimize the code differently and will optimize differently than when you do a new line and say string buffer.append. Therefore, this code is slower because the other code is optimized by the compiler way more than the non-fluid version. So the fluid one is actually faster, and nobody would ever thought of that initially. You can see that the sized one is kind of slightly faster and burns slightly less memory. The sized builder here is comparable to that one. It's kind of 8K, burns the same. Concatenation and plain. Plain is not that bad at the end of the day. But once again, what's wrong with that benchmark? Just give me answers. It's the wrong one, it was the wrong question. Guess, please. What's wrong with what I have done? The benchmark itself is correct, by the way. There's one assumption I made which is wrong. Correct. I made data assumptions. I made fixed data assumption. So let me fix this and make something different. So I have a lot of data, a lot of different sizes. And here I have this foo method, and it gives me basically randomly one of these strings. And when I basically run a concat foo, I get one of these. So kind of randomly, evenly distributed, so should be always kind of predictable. So let's run this. And as you can see here, suddenly things change. The builder is 40, non-fluid 37, non-fluid 22. So this difference here, which we saw before, is not longer there. So if it's big enough, nobody cares. And finally, the plain one is way faster than the builders. So a string a plus c, or a plus b plus c, is not bad. You can do this in your code, especially when you have a database as a backend. Nobody cares. Here in this case, really it's about the data. If you have enough data and you concatenate it, nobody cares if this is a builder or not. But of course, if you have a loop, and in this loop you concatenate to a string a lot of objects, not just a plus b plus c, but something you kind of, let's say you build a CSV line based on kind of a lot of data, and this might have 18 elements. You will do, or you have to do a string builder, otherwise you just create a lot of garbage, because every new string is basically a new instance, which is kind of new allocation, stuff like that. But the internet is wrong. The internet says you always have to do string builder, which is not true. There are so many examples you can create where string builder is slower at the end of the day. Good. Still 20 minutes to go, and there are still a couple of slides left, but I would like to use this moment to ask the question if you have any questions, because I bombarded you with numbers. Sorry for that. I hopefully gave you a couple of insights how the VM actually works and how easily you can, I wouldn't say kill yourself, but make your evening miserable or your next production deployment or whatever you have to do. So if you have any questions.
So you've shown us that this is incredibly variable depending on what you put in. It's variable between runs. It seems super duper flaky. So I must ask then, what is the point? What can we use microbenchmarking for if it is so seemingly unreliable?
I hopefully also have shown a couple of examples which are kind of more reliable than the others. Obviously, you always have seen the bad stuff. If you know your data, if you know your setup, and you pay proper attention to warm up the machines you use, you have always enough runs for comparison, you might have the right hardware, most of the results are usable. Unless you want to do something like, let me remove 1 or 2 instructions and try to see if one is faster. Because this micro-optimization might not be measurable at all.
And when you say the right data, the right hardware and stuff, you mean the right as in matches the real problem as opposed to is well aligned with the microbenchmark.
Yeah. And there's a slide for that in a second. Any other questions?
Immutability takes more time than mutable
Yeah.
objects. How should we qualify?
Have a problem, and then you can look for a solution. So the general thing is obviously mutability and immutability are 2 sides of the same coin. So immutability means never change anything you created before, like records, for instance, they are immutable. Strings are mutable. And this is the functional pattern, and this is the pattern you are supposedly to use when you do concurrent programming, because it's kind of easier to handle data that never changes. But of course, if you create data, and for a slight change here, you have to copy it over and do a new one. As you have seen, you spend a lot of time just doing copy operations and new operations and garbage collection, stuff like that. I have an example, and if I have the time, I can show you, for the one BRC challenge. This is a talk that's not in this conference. When you start doing this with the naive approach, you churn about 200 gigabytes of memory just to do this challenge where you read a CSV and you do calculations. While optimizing, 320 I think was the starting point. While optimizing and tuning it, I get to a point where I don't create any new memory. I don't need any memory. So the entire program with 1 billion lines of 13 gigabytes of data runs on a 4 megabyte virtual machine. Super fast. So we got down from 320 gigabytes of memory churn when you program like you would program, as you have seen in presentations and read in books, to think about it, and you just need 3.7 megabytes instead to run the entire program. You can disable the garbage collector for this, and it still runs fine. By the way, you would say, okay, this is an artificial example. It's not. Traders trading at Wall Street is done with Java programs. And what they do there is they write code as they would write C code, but in Java. So they allocate everything they need up front, and they will never reallocate because this is latency, this is overhead. If you want to have predictability in a fast program, you have to be mutable. And then you get something where there's no garbage collector, you can turn it off. Does it answer your question? Thank you. Any other question?
So we had a slide where we toggled the inline flag.
Yeah,
Compiler.
inline flag.
Is there also inlining during runtime, or is the flag only for
No.
compile time?
First of all, there's a common misconception that's based on how Java started. There was a -O flag when Java was very, very young. And this -O flag looks like the -O flag from C. When you basically tell the compiler -O, it starts to optimize your code. This flag still exists. This flag doesn't do a thing since version 1.5 or something like that. Java doesn't do any optimizations during compile time, so 2 bytecode, besides constant folding, where it basically says, oh, I can already do 1 plus 1 because it's 2. That's the only thing it does. And everything else happens during runtime. Obviously, we talk about OpenGDK here, not the Graal binary version, but it's just during runtime. It will just look at the code that's there. It will start to produce a version. And if it doesn't like the version because it's slow, it re-optimizes it again and again and again. And the inlining here also starts as no inlining at all. And then it sees, okay, I produced a method that's only 5 bytes. It's really, really small. There's a lot of overhead. So take the significant 5 bytes and put them where they have been called for or will be called from. And then you have basically another method that might be 10 bytes. And it's like, okay, let's inline this and inline that. So at the end of the day, your stack basically becomes shorter. And this is inlined until there is a method that's big enough. So we won't inline anymore. You can tune this, but I would not recommend this because you can only do things wrong. At the end of the day, even so, there are a lot of compiler flags, JIT compiler flags to say, do it 45 bytes or 90 bytes or something like that. It doesn't change a thing. Okay. Another question?
Speaking of inlining, kind of a digression perhaps. So you do inline method bodies and stuff like this until you get to a size that's too big when you say I can't inline this anymore. And this will normally be on method call boundaries and stuff. Is there anything in the JVM that will go, hey, I've inlined this, but it looks like I can actually turn these things into methods. They weren't before.
No.
I'm going to make
There's
virtual methods.
no, we don't do also, compiling always happens on method level. You can't compile anything else than a method unless you are a loop. Then you can see this loop body as a method.
Yeah.
So Java can on the fly do kind of optimization there. The inline things will always kind of inlined. They will never form its own new method. So this different pattern doesn't exist. So we are only going one way or the other. Any other questions? And then I will happily bore you with the rest of my slides, which summarizes what we have seen before and might also answer one of your questions. And this is, of course, my screensaver, which explains what kind of OS I'm running. Okay, so microbenchmarks. What's your motivation? This is the first question you should ask yourself. What the heck? You know what microbenchmarks are. You already know how complicated they can be. The question is, do we really need to write a microbenchmark? So you might have a production problem or oddity. You might have an idea or suspicion for something. Or the other one is a colleague told you, that's the famous, I read this on Medium, or told to make it scale, like a boss drops by and says it has to run twice as fast. We basically want to save a machine or two. Or, it's way too expensive, try something else. When you have a production problem, you're supposed to profile this problem in production first. You might have an idea, but this assumption might be totally wrong. You might prove your idea, the bias, remember I told you about the bias? You might have a bias towards a certain solution because you might actually like this solution, because the code is not your code, it's from your colleague. And of course, the code from your colleague, I don't like it, because everyone is its own, kind of poet in terms of how code should look like. And therefore, you come up with something that's immediately obvious to you, but doesn't do a thing, or might just do the opposite. You have to benchmark most of the things before you actually micro-benchmark. Benchmarking means if you have a production server, Spring Boot application, for whatever reason why I come up with this, but Spring Boot application, run a real benchmark against it. Do load and stress test and see what you get. Measure, see that you can measure something predictably, and then you might profile it, run OpenTelemetry, or any other things. You might just kind of async profiler is a really good profiler if you want to look into some details of the VM, and then just give you an idea in which direction it goes. This method is hot, or we churn too much memory. You need a first idea before you go into microbenchmarking. If you have kind of a strange goal given, you also have to profile first. You might have to make up this problem before you find a solution. Don't find a solution and benchmark this one. Benchmark the problem first, micro-benchmark the problem first. Create the problem, and then you improve it. Um, if you have no idea, then don't benchmark. No idea doesn't mean you have to spend any time on it. If you don't have a sound theory about what you want to do and why you want to improve it, just forget about it. It might not be a real problem at all. So come up with a benchmark first. If you don't have enough for a micro benchmark, come up with something, just maybe something stupid first. And then from there, you go into details. Things you might want to change or look at is algorithms, kind of your code, memory allocation, freeing access. We have learned memory access is insanely expensive. Cache is your friend. Not hitting the cache is obviously an anti-pattern. External dependencies, I/O for instance. And then of course scale, synchronization prevents scale, or CPU usage. So for instance, you're hitting a machine with 8 cores and 4 of them are virtual threads. And it doesn't scale. Obviously it doesn't scale because these are virtual threads. Try it with 4 with 8 real cores and see what you get. And then maybe develop something you can improve on. Get rid of the crappy hardware first, see what you can take from that, and then continue. And then, of course, think about the interaction of your component with the world. This might be why this problem exists in the first place. If I rip out of my engine from the car and put it on a test bed, it might be great, but as soon as I race around the track, it doesn't work, because you might have forgotten about the interaction with the world, which could be the transmission, for instance, or maybe the fuel system or whatever. So always come up with a kind of an idea and see where things are connected to. Isolate your problem. Don't rewrite the code entirely. Just maybe see if you can take the production code and just give it a benchmark API and see that the data also flows naturally. Don't remove code in the first place because you think, hey, this is not important for the benchmark at all. Obviously, if it's not called, it's not called. But other than that, it doesn't cost to have more code in your code. It just might look a little kind of cluttered, but that's it. Data preparation, isolation is really important. There's the code that runs, and there's the data you need for it. And production is also kind of isolated from each other. Do the same. The standard GMH prepares data only once, so it's really difficult when you have to mutate something. That might be one of the problems where you allocate more than you can actually measure, because, for instance, for sorting, you have to redo things again and again. It's really difficult to come up with something you can measure reliably. But in production, you might also be just doing exactly the same thing. You always get new data, you mutate it, and then you return it. So maybe that's okay. If you have concurrency problems, these tests, these benchmarks are really hard to be composed. So it's really hard to come up with something that works. I kind of skipped the entire part of concurrency today because it's really, really its own deep dive at the end of the day. And your initial test case, your initial benchmark, don't change it. Always keep it around as the initial benchmark, the one you are comparing to. And have always unit tests that prove that the code you have there is actually doing what it's supposed to do. I honestly spent slightly over a week on code which was running extremely fast and nice until I realized that it's not longer doing what it's supposed to do. It all looked so good, overall spot checked, everything was cool, but it was so optimized that I basically missed the main path and it was just doing nonsense. But I was very happy with the nonsense at the end of the day because it turned out to be very fast nonsense. Okay, data. Once again, think about amount, size, structure, layout, and variance of your data. Don't. If you have static data in your test, but dynamic data in the sense of it's always different in production, change this. If your data from production contains, let's say, erroneous data, like empty lines or things you can't parse, this has to be in your test data. Maybe you can come up with something like clean test data, garbage test data, real test data, and you might see a difference. Why not? But don't forget to have this real data flow. And as you have seen with the exception, it can drastically change performance. Because your data might be actually the problem, not your code. Good. Execution profile, think about when the code runs, startup, cool. Occasionally, always. Occasionally is really hard to reproduce, so it's kind of where you basically play against your machine. You try to come up with something that makes sense. Always keep the cold one and the hot one for reference and try to find the middle ground. And then, of course, we have the error or rare pass at the end of the day. Then, of course, you have the problem that you might have code that's so small that at the end of the day it will be inlined into another method. And if you run these benchmarks, you might not have inlining at all. So you measure the method overhead, and you get a runtime that's not real anymore. And this one is really difficult. But there are certain flags you can use on the VM to actually give you an idea if your methods are inlined and where they are inlined. They could be inlined several times in several places, so your code actually gets duplicated. So keep an eye on it. Good. Oh yeah, here the one. Unit test. Have unit tests, please. Unit test as many unit tests as possible. Make sure you're not doing any garbage work. It's really embarrassing at the end of the day too, to be honest. Good. Question your own results all the time. Typically, the problem sits in front of the computer. It's not the computer. It's not the software. It's rarely the compiler. It's mostly you. Obviously, GK is not perfect. It's also buggy, but it's probably not as buggy as you when you think to outsmart the compiler to a certain extent. Think of edge cases, come up with something, and make sure everything is covered. And then when you have a result, vary your data, vary how you execute, vary the machine, vary the size. Play with it and see if this gives you different results, if this ensures that your theory is sound at the end of the day. Good. And then you have, of course, all the tooling, where you can do certain things with the GMH, garbage collection, investigation, the performance counters from your machine. You can do perf RSM, that gives you basically the hotspot in assembler of your program. You have to read assembler at the end of the day. It will really mark how many % of time are spent in this line. You will sometimes see that you do memory access because this line is really expensive. This might be the clue to the solution. Class loader, JIT compiler, you can do a lot. By the way, the last one, async profiler. If you have not used async profiler, that's the time to use it for the first time. Async profiler is, for me, the greatest profiler on earth. It's free, open source. It's really useful, and it plugs in really nicely into GMH. And why it's so useful? Because you can even do things like give me all the locations where I miss the L1 cache. Give me all the locations where I have most of the instructions in my code, or where I access the memory more often than here and there. This is something other profilers typically don't tell you. Good. Ask someone you trust to review what you have done. Peer review, always cool. But don't turn it into a pull request that gets just approved by someone glancing over it. Someone else should be interested in what you have done. Otherwise, it turns into we'll see. Okay. Verification by knowledge. You learned a lot. Apply this knowledge today, from today to your work. And then there's one thing. Microbenchmarking is good for isolating a problem, investigation, tuning, detailed tuning, squeezing the lemon. It's really bad for general conclusions, black and white comparisons like always do string builder, large scale impacts. Typically, if you already are into microbenchmarking, it's not that you might change things dramatically, because if you can change something dramatically, you don't need a microbenchmark. If you basically can double the runtime just by doing index off instead of split, this is not a microbenchmark topic. And don't be an impatient developer, because that will lead to problems. Conclusions. It's okay to do microbenchmarks. You are a GDK contributor all the time. Open source contributor all the time. Your problem can be isolated, cool. You have to isolate for easier tuning. You're cool. You want to debunk your colleagues' claims, also cool. You're just curious, yes. If you want to write a Medium post, don't do microbenchmarks. If you want to tune something in production without a need, don't. And if you swipe left on all previous slides, also don't do microbenchmarks. I think it's left, right? I don't know. Good. One last thing, and this is the warning from GMH itself. I just summarize this quickly. Whatever you do, it's wrong. Question it, what you have done. Try to come up with ideas and try again. Okay. That basically means Q&A and 10, oh, I'm 11 seconds over. I'm so sorry. Thank you very much for your attention. If you have any further questions, please come down. Other than that, have a nice DevOps and see you soon.
All systems are nominal. Initialize Genesis.